Well, let's pick up here. I think we had just done this one, right? Okay, so we're talking about double replacement reactions, and basically we're double replacement. So two things are being replaced. So like this one, we took barium with chloride, sodium with sulfate, and we swapped it. We made barium with sulfate and sodium with chloride. So that's all you do is you just swap them out. Okay? Let me do one more here real quick. So sodium chloride and lithium nitrate. So help me out here. Let's write out what is the formula for sodium chloride? NaCl, and it tells you it's aqueous. But if it didn't tell you it was aqueous, you should still know why. Because it has sodium. So anything with sodium, always soluble, no exceptions. Lithium nitrate, what's that formula? LiNO3. And it tells you again that's aqueous, but if it didn't tell you, how would you know? Lithium and nitrate. Nitrate. Anything with nitrate also always soluble, so you would know if I didn't tell you. Okay, so we're going to swap. We're going to do a little switcheroo here. We're going to trade out the chloride for the nitrate. So, if I put sodium now with nitrate, what would I get? What's the formula for sodium with nitrate? Again, you can't just trust, oh, it was one there, one here, right? But you can't do it that way, right? So, right, it's always charges. So, what's the charge on sodium? What's the charge on nitrate? Put them together. So, what is it? Yeah. So, I'm sorry, what's the formula? Yeah, just NaNO3. Yeah, one of each. Good. Okay. And is that one soluble, aqueous, or is that insoluble, solid? Aqueous or solid? Aqueous, because it's got sodium, which is always soluble. It's got nitrate, which is always soluble. So it's definitely soluble, aqueous. Plus, what else do I make? Lithium chloride, yes, which is what? LiCl. And is that aqueous or solid? How do you... Okay, so both. I heard both. Aqueous. Why is it aqueous? It's all those group ones, lithium, sodium, potassium, they always dissolve, so aqueous. Good. Oh. Well, is there anything special about this reaction you might have just noticed? No reaction. Why? They're all aqueous. So if they're all aqueous, well, really all that happened was you dissolved up sodium and chlorides and lithium and nitrates, and over here, they're still just swimming around, nothing combined. So you have to have at least a solid, a liquid, or a gas somewhere. We don't, so no reaction. Nothing happened on that. Good job. You figured it out. Okay. Well, your turn. Get out your hand out there and try the first one. Take aluminum acetate, put it with potassium sulfide, swap the partners, use your solubility rules to know if they're aqueous or solid, and see if there was a reaction. If there was a reaction, then balance it out. If not, just write no reaction. Get out your periodic table. I'll pull this one down too, but if you have one hand. Yeah, help each other out. What's aluminum acetate? Ask your neighbor if you don't know, What is the next one? Potassium sulfate. And what's the charge on aluminum? What's the charge on acetate? Make them balance. What's the charge on potassium? What's the charge on sulfate? Make them balance out. I've seen several people have the wrong formula for aluminum acetate. What's the charge on the aluminum? 3. What's the charge on the acetate? 1. So you can't have 1 to 1. You can have 1 aluminum and 3 acetates then. Now, what's the charge on K? What's the charge on sulfate? I mean sulfide, sorry. So, put them together. Point H. There you go. I mean, I can probably find it.
That's fine.
Yeah, 8.8 right there. Again, you gotta memorize those. There's only 5 rules, really. So, okay, well, let's go over it. Let's go over it. So, what's the formula for aluminum acetate? Al parentheses. Okay, good. Is that aqueous or solid? Because it tells you, but if it didn't tell you, how would you know? Acetate. Anything with acetate, always soluble, no exceptions. Potassium sulfate. What's that? What's the formula? K2SO4. I'm sorry. It's not sulfate. It's sulfide. I'm sorry. Yes, sulfide. Sulfide. So ide. There you see ide. Non-metal by itself. So soluble, we know, but how do you know it's aqueous? I mean, it tells you solution, but if it didn't tell you, potassium, lithium, sodium, potassium. Any of those group 1A's, soluble. Okay, now we're going to swap the acetate with the sulfide. So what am I going to make? What's the first product? Aluminum, yes, with sulfide, Al2S3. Aluminum's 3 plus, sulfide's 2 negative. So again, I'll say it again. You can't just say, oh, it's 1 aluminum here, 1 sulfur here. It must just be ALS. You got to use the charges, right? 3 plus, 2 negative, make them balance out. Solid or aqueous? Solid. Yes. Because neither aluminum or sulfide isn't one of those 5 rules, so everything else is solid. And what else do I make? Potassium acetate, correct, which is, what's that formula? KC2H3O2. Aqueous or solid? Yes, all potassiums, all acetates. Now I just want to point out, notice the state does go right after the formula. Please don't be writing like solid or weird places like that, else you will get marked wrong on the test. So just goes right after it. So this should be a picture right here, but I ran out of room. Okay, so good. So yes, so there is a solid. So yes, there is a reaction. How do I balance it?
2 aluminum acetate.
2 of these. 3 of these. 1 and 6. Good. All right. Let's try another one. And I'll go back and I'll go back to those solubility rules in a second, so you can see them if you didn't get them down there. Okay, so I'll write down the equation if you don't have the handout. Hopefully you do, but no. Peek back at the solubility rules for those that need to write them down again. Barium chloride and sodium carbonate. Barium chloride and sodium carbonate. Okay, so let's try this out. We got barium chloride. That's BaCl2. And that is aqueous. It told you this time, but if it didn't tell you, you should know, because all chlorides are aqueous, except with silver, lead 2, or mercury 1. Sodium carbonate. What's sodium carbonate's formula? Yep. And it tells you solution. But if it didn't, you would know, because why? Sodium, yeah, anything that has sodium, aqueous. Okay, so now we swap that chloride and that carbonate, make a new compound. So we're going to make barium carbonate. What's barium carbonate? Solid or aqueous? That's solid, yes. And then sodium with chloride, what's that? NaCl, solid or aqueous? Aqueous, of course, anything with sodium. And how do I balance it? 2 NaCls. Okay. Woohoo! Okay. One more. Try that one. Lithium phosphate and potassium sulfate. Yes, everything is aqueous, so no reaction. Let's try it out here. Lithium phosphate, Li3PO4. Anything with lithium is soluble. Potassium sulfate, K2SO4. Anything with potassium is soluble, so aqueous. Swap them, lithium with sulfate. Anything with lithium is soluble, aqueous. Potassium phosphate, K3PO4. Anything with potassium is soluble, so aqueous. So you could balance it if you want, but you don't really need to because there's really no point because there was no reaction. Because everything's aqueous. You got to have at least a solid, a liquid, a gas, something besides all aqueous. Okay, well, what I've just shown you is the complete equation. This is what we call the full chemical equation or the molecular equation. And that's everything. That's the entire molecules, everything that's there. Okay? So that's what I just showed you how to write. But now I want to kind of start to break it down to show what's going on with the ions. Because again, if this is aqueous, that really means this is already dissolved, and it's made silver ions and nitrate ions, and it's made potassium ions and chloride ions. We're going to write what's next called the complete ionic, where I'm going to do that. Anything that's aqueous, I'm going to break it up into its ions. I'm going to break it up in its ions. But solids, liquids, gases, those really are together, so those I just bring right down. So you don't break up solids, liquids, and gases. Basically, so we're going to have the molecular or the full equation, which is just the ones you were just practicing writing. Then we're going to write the ionic. So we're going to take anything that's aqueous and split it apart to clearly show the ions that are present. Okay, so that's the next kind of equation. So this is kind of helps us to see what's really going on. Okay, and then once we have the complete ionic, I'm stalling so you can write that down. Then we're going to write what's called the net ionic, which is the third equation. I'll wait for you to finish writing on that equation. So in the net ionic, I'm just trying to focus in on what actually went on. Because you see there's some ions that go in on the left side and they come out on the right side. They didn't actually do anything in the reaction, right? Do you see that? Which ions are on both sides and didn't actually do anything? Potassium's just swimming around over here. Still swimming around, didn't do anything. What else didn't really do anything? The nitrate didn't really do anything. It was just there to bring along the silver. The chloride was just there to bring along the potassium. So those we call spectator ions. So we don't really care about those. We're going to cross those out. And then what I'm left with, that's the meat of the reaction. So what actually did something? Oh, the silver combined with the chloride to make silver chloride. And that we call the net ionic. The net ionic. We're going to cross out any ions that are on both sides of the net ionic. So we have the full equation, the ionic equation, and then the net ionic equation. So spectator ions, or any ions that are on both sides, we're going to cross them out. So again, this is what's really going on. What's going to happen? A silver found in chloride made silver chloride. The rest were just spectators. They're just like, yay, silver chloride, get it done. They're just like hanging out there, just cheering on, making it happen. They're not actually doing anything. They are the bench warmers. They're still paid millions of dollars for sitting the bench, probably. So, okay, so let's see here. So let's try one of these, and let's do all 3 3 parts. So hopefully you have your handout for this one because it's already labeled on your handout, full ionic, net ionic. So the first part is the thing we were just doing. We're going to write the formulas, swap the products, all that good stuff. So help me out here real quick. What is the formula for iron 3 bromide? Iron 3 with bromide. F. I'm going to change colors here. I'm tired of my red. FeBr3. Aqueous or solid? How do you know? Bromides are all aqueous, except with silver, lead 2, or mercury 1, which is not one of these, so yes, aqueous. Potassium phosphate. What's potassium phosphate? K3PO4. Good. Aqueous or solid? Why? Potassium. Anything with potassium. Okay. Let's swap our partners. So swap our bromide with our phosphate. So iron 3 phosphate. What would iron 3 phosphate? What? FePO4, a 3 plus and a 3 negative, so just one of each. Good. Solid or aqueous? Solid. Yes, solid, right? Because there's no rule for iron, there's no rule really for phosphate, so solid. Potassium with bromide. KBr. Solid or aqueous? Anything with potassium is aqueous. Good. Okay, let's balance it. 3 potassium. Okay, there you go. So that's the full equation. That's everything. That's the molecular equation. That shows them as the molecules. So now we're going to write the complete ionics. We're going to take anything that's aqueous, we're going to break it up and clearly show what ions are swirling around in that beaker, what's going on. So when FeBr3 breaks up and dissociates, we call that, what ions will it make? Fe3 plus, aqueous. You're exactly right. What else will it make? How many Br negatives? How many Brs are in there? It's going to make 3 Br negatives. Right? Because it broke up and it made an Fe and the 3 bromides. Okay? How about the K3PO4? What will that dissociate into? 3K what? 3K pluses, because potassium's plus. And what else? PO4, 3 negative. Good, awesome. So it's drawing a little arrow there, just kind of show you, right? So this became that. This broke up into that. Good. Okay, how about FePO4? Just stays the same because it's a solid, right? We don't break apart solids, so just write it again. FePO4, parenthesis, S, parenthesis. Okay, 3 KBRs. What ions will 3 KBRs make? They'll make 3 K pluses, aqueous. And what else? 3 Br negative, aqueous. Awesome. Again, it was 3, so 3 potassiums and 3 bromides. Okay, so that's the complete ionic equation. So now you can see everything the way it kind of is in the beaker. So initially you had that swimming around. Afterwards, this was formed and this is still swimming around. So, for the next one, the net ionic, we're going to cross out anything that is a spectator ion. So which ions are present on both the left and the right? They didn't do anything. They're just cheering on the team. Bromides. I see 3 bromides, 3 bromides. Potassiums. 3 potassiums, 3 potassiums. Okay, so this is a little helpful note. You should always be crossing out the same numbers on both sides. If it's ever like 3 bromides and 2 bromides, then you didn't balance something right and something's wrong. Okay, so go back and find your mistake. But it should always be, if it's 3, it should be 3. So it should never be like 1 and 2 or whatever. Okay, so now we're going to write the net, which is just whatever's left. So what's left? Well, iron 3 aqueous is left, plus phosphate aqueous is left. Oops, goes to iron 3 phosphate solid. So that's the net ionic equation. That's what was left, right? Iron 3 phosphate goes to iron 3 phosphate. Got it? Maybe not. Let's try one. Let's see. Try ammonium carbonate and copper 1 sulfate. So write the full equation like we have been. Then anything aqueous, break apart. And then cross out your spectators and write what's left.
See that trailer? Is that new trailer?
I just saw it, yeah, a while ago. Yeah, like an hour ago.
Awesome.
I had a friend posted on Facebook, I guess there was some big convention today in Anaheim.
Yeah.
They had a big panel with the old cast and the new cast. And so he was watching it live. Now it's up to watch the recording, so I want to watch it. Okay, well, I'll write the molecular equation. Just make sure we got that part going the same. So NH4 in parentheses 2 CO3 aqueous, because ammonium is always aqueous. Copper 1 sulfate Cu2SO4, aqueous or solid? Aqueous, because sulfates are all except for, what is it, barium, calcium, strontium, lead 2, I think. Let's swap them out. Ammonium sulfate. Ammonium sulfate. Anything with ammonium soluble, so aqueous. And then plus copper 1 carbonate, Cu2CO3, and that's a solid. And it's already balanced, right? Okay, so take that and make the complete ionic equation. Anything aqueous, you should break up into the proper ions. Make sure you have charges on your ions, you have the states. So, see what we can come up with. So anything aqueous, I'm going to break apart into the ions. So ammonium carbonate, that's going to make 2 ammoniums, NH4 plus. Don't forget the charges, that's the thing that everybody always forgets. And a carbonate, CO3, 2 negative. Cu2SO4, that makes 2 Cu pluses, aqueous. And a sulfate, SO4, 2 negative. And that goes to, I guess we'll start a new line down here. Ammonium sulfate, that makes 2 ammoniums, aqueous. And a sulfate, 2 negative, as aqueous. And then the solid, just leave together as a solid. Okay, how'd you do so far? So far, so good? Okay, so what do I cross out? Which ions are on both sides, not doing anything? 2 ammoniums, sulfate, sulfate. Okay, so those are the spectator ions, ammonium and sulfate. So just rewrite whatever's left. Carbonate, aqueous, plus 2 copper, aqueous, goes to Cu2CO3 solid. So that's what was left. The order doesn't matter. You could have had the coppers first, then the carbonate. It doesn't matter as long as the reactants are on the reactant side, products on the product side. Okay? Questions on that? If you made a mistake, did you find your mistake, maybe? Okay, let's try one more. Calcium sulfide and tin-4 acetate. Calcium sulfide and tin-4 acetate. So, calcium sulfide. What's the formula for calcium sulfide? Solid or aqueous? Solid, actually, yes. There's no rule for calcium or sulfides that we have. Tin-4 acetate.
SN parentheses C2H3O2 parentheses 4.
Good. Solid or aqueous?
Aqueous.
All acetates are aqueous, so yes. We're going to swap. I'm going to make calcium acetate. So that'll be Ca parenthesis C2H3O2 parenthesis 2 aqueous and tin-4 sulfide. What's that?
SNS.
SNS2. Reduce it to the lowest ratio. 2 to 4 can go to 1 to 2. Solid or aqueous?
Solid.
Okay, balance it.
2 calcium.
Yep. There you go. Okay.
And 2 calcium.
And
acetate.
2 calcium acetates. There we go. All right. 2 calciums, 2 calciums, 2 sulfurs, 2 sulfurs, 1 tin, 1 tin, 4 acetates, 2 times 2, 4 acetates. Okay, let's break apart anything that's aqueous. So calcium sulfide is not aqueous, so I'm going to just write it again. Tin-4 acetate, that's aqueous, so that'll make tin-4, which is SN4 plus, and 4 acetates. So 4 C2H3O2 negatives. 2 calcium acetate aqueous. Oh, that'll make 2 calcium ions. And then 2 times 2 acetates, so 4 acetate ions. And then the solid we leave together. Plus SNS2S. Alrighty. What's our spectator ions? 4 acetates, 4 acetates. Again, if you don't have the same number on both sides, you did something wrong. Like it was 4 and 2 or something. That's your little, like, whoops, something happened. So just write whatever's left. So 2 calcium sulfide solid plus tin-4 ion aqueous goes to 2 calcium 2 plus ion aqueous plus tin-4 sulfide solid. Okay, looks like fewer of you got that one than the previous one. So how can I help? Where's your questions? What? Something we can work on? Is what? Only with sulfate there's a rule for it. Yes, there isn't a rule, so everything else there's not a rule for is solid. So those 5 things there's a rule for are the aqueous ones. Everything else is solid. So there isn't a rule for sulfide, so solid, unless it's with lithium, sodium, potassium, ammonia.
So then shouldn't it have been solid?
Where?
Calcium.
It was calcium acetate. You got to start with what it was. You bring it down from what it was. Yeah. Yeah, so don't change it. Yeah, but it's a very common mistake too. It was aqueous here, then calcium by itself is solid. They'll start making it solid here. No. Keep it the same state it was here. Bring it the same state all the way through. Yeah. Okay. Well, we're going to talk about. So when you have something dissolved into water, let's say it's calcium acetate dissolved into water. Well, you might want to know how much, and that that amount, that how much is dissolved, is termed the concentration. So in a very qualitative sense, a general term is to say it's dilute, which means there's not much of the solute dissolved in the solvent. Dilute means there's a relatively small amount of the solute. And if there's a lot of it, let's say it's, it's salt water and it's really salty, or there's a lot of sugar in your coffee or whatever it is, then you say it's concentrated. So that means you have a relatively large amount of solute compared to the solvent. So yes, if it's dilute, you only had a little bit compared to how much there could have been. It's concentrated, yeah, there's a whole lot in there. But obviously, again, like I said, that's a very qualitative term. It's much easier if you actually put a number on it, right? Like there's so much of it in there. So there's a few different ways we can put a number on that. We're going to look at just one today. And it's going to be percentages. You've all seen percentages before in this class, other classes. The percentage, anything you're looking at for a percentage. Percentage of, percentage of girls in this room, percentage of quarters in your pocket, percentage of, whatever, Texan fans, or whatever it is. It's just the part you're interested in divided by the whole times 100. The part over the whole times 100. So if I want to know, let's say it's the percent sodium chloride in the solution. The part I'm interested in, the solute, over the whole thing, the whole solution, the solute and the solvent, times 100. So any percentage, the part over the whole times 100. So in our case, solute over solution times 100. And remember, the solution has two components, right? The solute plus the solvent. So the part over the whole times 100. So now this one is called mass percent. Notice it's M/M because both of these are masses. There's a mass on the top, there's a mass on the bottom. Mass percent, we call that. And then I'll show you a couple other ones. We're going to use volume. We're going to use mass and volume. So MM means mass on top, mass on bottom. Mass per mass. Mass per mass. Okay, now the only other little thing to follow in the back of your brain is both the units have to be the same or they won't cancel. So if solute's in grams, solution has to be in grams. If solute's in milligrams, solution has to be in milligrams. If solute's in kilograms, solution has to be in kilograms. As long as they're both the same unit, you're good. They're going to cancel, okay? Okay, so let's just try one. Let's say you're in the lab and you take out 5.00 grams of sodium chloride. You dump it into 97.0 grams of water. You stir it all up. What percentage of a sodium chloride solution did you just make? Well, we're going to take the mass of the solute over the mass of the whole solution times 100. So, let's try that out. So, what's the mass of the solute for this one? Oh, you hate sig figs, don't you? 5.00 grams. Okay. Sodium chloride over what's the total then? 5.00 plus 97.0, right? So I'll just write it in here the first time. Grams times 100. So yes, 5.00 grams NaCl. And there was a total of 102.0, because tenths place and hundredths place has to be tenths places if you wish. That's the whole solution times 100. And it's like, 4-something%. What is it? 4 point what? 90. There you go. 3 sig fig sounds better. So yeah, it's 4.90% sodium chloride, right? That's the percentage of the solute out of the total. Okay. Yay. Your turn. Take 3.9 grams of ammonia, dissolve it in 65.0 grams of water. What's the mass percent of the ammonia? Okay, ask your neighbor. What did you get? Ask your neighbor. Okay, 3.9 grams on top of ammonia. Ammonia is NH3, by the way. Over the total, which is 68.9 grams of the solution, right? Times 100, so what'd you get? 5.7%. There you go. So that's the percentage of ammonia in that solution. Okay? Okay, I'm gonna skip that one. Now, you don't have to use mass. You can use volume. So, for example, let's say you read the percent alcohol on a bottle of beer or a bottle of whiskey or something. It'll say, it's 8% alcohol by volume. By volume. They're doing volume percent. The volume of the alcohol compared to the volume of the whole bottle of whiskey or the whole bottle of beer. So, now it's still the same thing, though. The part you're interested in, the solute, over the whole solution, times 100. The part you're interested in, the solute, over the whole thing, the solution, times 100. And again, just make sure, though, they're both in milliliters, or they're both in liters, or whatever. They both have to be the same unit, okay? So let's say it's said on that bottle it's 7% by volume, I don't know, alcohol, or whatever it is. 7%, right? A percent means out of 100, right? So that would be, there's 7 milliliters of alcohol for every 100 milliliters of beer, or whatever it is. Are you with me? So yeah, so just the part over the total times 100. And percent's always right out of 100. Okay, let's try one. What's the volume percent of bromine in a solution prepared by dissolving 12 milliliters of bromine in the solvent carbon tetrachloride to make 250 milliliters of solution? So read that carefully and figure that out. The solute over the solution times 100. The solute over the whole thing times 100. Okay, so what'd you get? What's the percentage of bromine in that solution? 4.8. Anybody else? Okay, so what goes on top? What number? 12 milliliters of bromine. And what's the total solution? 250, right? So it's not 262. You don't add them together because it's not 250 milliliters of the solvent. 2 milliliters of the whole solution already, right? They already gave you the total this time. Good. 250 milliliters of the whole solution. So times 100 because it's a percentage. And I'm sorry, what was the answer did you say? 4.8% bromine. Good. Okay, perfect. Let's try this one. Calculate the amount of solute in milliliters needed if you want to make 225 milliliters of a 15% by volume isopropyl alcohol solution. So a little different. So now they're not giving you the solute. They want to know how much solute do you have to dissolve up to make a 15% solution. So we want to make 225 milliliters of solution, and we want it to be a 15% by volume solution. So let's think about what we know. So I know 225 milliliters, put that down here, of solution. What does 15% mean? That means there's 15 milliliters out of every 100 milliliters, right? And it's VV, so I'll put both the milliliters. Well, 15 milliliters of what on top? isopropyl alcohol. Write the thing you were dissolving. So I'll put isopropyl. Or you could put alk, or I don't care, whatever. Over 100 milliliters of what?
Solution.
The whole solution. Okay, good. So I want solutions to cancel. So I'm going to put 100 milliliter solution on the bottom. 15 milliliters of isopropyl on the top. 100 milliliters of solution has 15 milliliters isopropyl. So I multiply through there. And how many milliliters of isopropyl alcohol would I have to use? How many sig figs? So how many?
34.
Right. So there you go. So that says, okay, so if you wanted to make 225 milliliters of solution, and you want it to be 15%, what would you do? You would go in the lab and you would measure out 34 milliliters of isopropyl, pour it in your beaker, and then add water until it's a total of 225. When you stirred it all up, voila, you would have a 15% solution. Okay. Now the other way we can do it is we can mix them up. And this is commonly used like in hospitals and things like that. Mass per volume. So for example, like a lot of times in a hospital, if you're going on an IV bag or whatever, it'll say 5% this, 3% that. But it's oftentimes, it's the mass of the solute, so how much powder they dump in there into that solution. The mass in the solution. So they call that M/V. M/V. Now, same thing. The part you're interested in, the solute over the whole thing, the solution times 100. But this one is picky. This one, since one's mass, one solution, it's got to be grams and it's got to be milliliters. So you can't just pick any, so you can't use kilograms of milliliters or grams and kiloliters or liters. You use grams, we're going to use milliliters. It's the same thing. Part over the whole times 100. Now the last two, mass per mass, as long as they're both the same unit, doesn't matter. Volume, volume, same unit, doesn't matter. Here, it does matter. It's got to be grams, it's got to be milliliters. Okay? Well, same thing. If I say it's 5% M/V, that means there's 5 M grams per 100 milliliters. Right? 5 out of 100. But now it's 5, mass, grams per 100, volume, milliliters. Right? Okay, let's try one. Calculate the mass per volume percent, MV, for the solute in 75 grams of sodium sulfate in 250 milliliters of sodium sulfate solution. So what's the percentage? You have 75 grams in 250 milliliters of solution. What's the percentage, the MV percent? So, what do you think? What'd you get? 30%. Okay, let's write it real quick. 75 grams of sodium sulfate. And the total was 250 milliliters of solution times 100. How many sig figs? So I'm going to put 30 with a point there to show that's 2 sig figs. There you go. Okay. Well, let's try another one now. We're going to use percentage as a conversion factor. So, how much solute in grams do I need to make 450 milliliters of a 2.0% solution? And it's mass per volume. So, how many grams of solute do I need to make 250 milliliters of solution if it's a 2.0% solution? I'm sorry, not 250, 450 milliliters.
Milliliters of solution?
Yep. So try that out. Think about that. So what does 2.0% mean, right? It means, what's it mean? It means 2.0 what? Grams per 100 milliliters of solution. So use that as your conversion factor here. Okay, what'd you get? How many grams of KOH would you need? 9.0? Okay, so let's try it out real quick. 450 milliliters of the total solution. And 2% means 2.0 grams of the solute, in our case that's KOH, over 100 milliliters of the total solution. What was it? I'm sorry, 9.0? There you go. So that's how much KOH you would have to use to make sure it was 2%. Awesome. Okay, I'm going to skip the next one just for time's sake. Let's look a little bit more at these percentages and how to use them. So I just showed you if you have a percentage, it means out of 100, right? So for example, 4.90 m/m, that means grams per gram, right? Out of 100, mass per mass. So that's the same as saying 4.90 grams of NaCl per 100 grams of solution, right? But of course, you can always invert any kind of conversion, right? You can always flip it over, 100 grams of solution per 4.90 grams of NaCl. Well, what if I don't care about the solution? What if I only care about the solvent? I want to relate the sodium chloride just to the water. How would I find the solvent out of that? Subtract, because this 100 is the total, right? That's this plus the solvent. So how much would the solvent be? 100 minus 4.9, right? 95.1. So I could also say, oh, that's the same thing as saying 4.9 grams of sodium chloride per 94.1 grams of water, the solvent. Or I could flip that, right? Well, I could also relate just the solvent to the whole solution, too. And get like that. So that one little percentage gives me 6 possible conversion factors out of it, depending if I want to know solute to solution, solute to solvent, or solvent to solution. It all depends what you want to find. Maybe the problem asks you to find how much solvent do you have to use, how much solution do you make, how much solute do you need. Depends what you're trying to figure out there. So let's try a few variations on this. We'll mix it up. Some solute, some solvent, some solutions. Okay. So here we go. Watt mass of a 5.00 mm%, so by mass, solution of dextrose contains 25.0 grams of dextrose. So here's a little IV bag, picture there out of the hospital. So basically they're saying you have a 5% IV bag here. Your patient needs 25 grams of dextrose. How many grams of solution do you have to give them to ensure they get 25 grams of dextrose? Are you with me? So how much solution do I have to give them to ensure they get 25 grams of the solute? So I'm trying to relate dextrose, the solute, to the whole solution. So I have 25.0 grams of dextrose. I'll just put dex because I'm going to run out of room here. Well, I want to turn dextrose into solution. How do I relate dextrose and solution?
Grams per 100.
5%. Yes, so 5.00% means what? There's 5.00 grams of dextrose per 100 grams of solution. So what do I put on the top? What do I put on the bottom? Dextrose on the bottom. How much dextrose? 5.00 grams of dextrose per 100 grams solution. So there you go. So I think I'm going to get, looks like 500 grams of solution. So there you go. So if your patient needs 25 grams of dextrose, you got to give them 500 grams of that solution, if it's by mass. Okay, let's try another one. What mass of solution would contain 50.0 grams of phosphoric acid if it was a 6.50% solution? So you have a bottle that says 6.50%. You want to ensure you get 50 grams of phosphoric acid out. How much of the solution do you have to use to make sure you get 50 grams out? So which one do I start with, 50.0 or 6.5? Yes, percentage is going to be a conversion factor between two different things. So I can't use a conversion factor first. I have to use the one that's just all by itself. So 50.0 grams, I'll just put acid, since you don't know the formula yet for phosphoric acid. So I have grams of acid. I want to find grams of solution. That's my goal. So how would I set this up? 6.50 grams of acid on the bottom, right? What goes on top? 100 grams of what? Solution. What's the answer? 769 grams of solution. Questions on that one? Okay, let's try one more. We've got enough time to do one more here. How many grams of solute would I have to dissolve in 20.0 milliliters of a 3.00% M/V calcium, what's that stuff called? Nitrite solution. So I have 20.0 milliliters of solution. I want to know how many grams of solute do I need. So what goes first, 20.0 milliliters or 3.00%? Okay, 20.00 milliliters of what is it of? The whole solution, right? I want 20 milliliters of the whole solution. So how do I use that 3.00%? What goes on top, what goes on bottom? 3.00, what's the units? It's MV, so M, grams, mass. Mass of what? Calcium nitrite, the solute, right? Over 100 grams of what? I'm sorry, not 100 grams. 100 milliliters, sorry, because it's MV of what? Solution. So what'd you get? Pardon me? 667? This is a little big. Divided by 100? 0.667 maybe then. I mean, I don't know. 0.600? How many sig figs should I have? 3. So what is it? 0.0600? You have confused the crap out of me. 0.600 grams of calcium nitrate. There we go. Okay. Alrighty, well.